I'm Keita from Shizuoka University, and thank you for giving me the opportunity to share our activity on our research activity. So today I'd like to share the high precision time-of-flight image sensor and system for the 3D application, 3D scanning application. Here is the outline of my talks. First, I'll briefly introduce the time-of-flight range imaging, and I'd like to explain why we'd like to develop the very high precision time-of-flight sensor, and then the key techniques. I'd like to introduce key techniques for achieving sub 100 micrometer range precision. As you know, the time-of-flight range imaging is an active method. So the camera has an image sensor and light source, and the distance between the object can be obtained by measuring the round-trip time. Round-trip time of time of flight by using this calculation. So the advantage of the time of flight ToF depth imaging is high speed and real time capturing, and then wide field of view or something like that. Here is a summary of the application of the 3D imaging for the ToF device. The horizontal axis is the range resolution or precision, and vertical axis is target range. The mainstream of the main target of the ToF device, especially the iToF device, is here. The application for the gesture recognition or input of AR device. So many people think that the ToF device is only used for the recognition use. This is because the time-of-flight camera, usual time-of-flight cameras has poor range resolution, the almost 1 millimeter precision at best. So we would like to open a new field. By using our techniques, we would like to open the new application of the time-of-flight device, and that can be applicable for the measuring field, such as inspection or response engineering. So in this talk, I would like to introduce this field, but in our lab we developed for the many applications. We developed the ToF cameras for the many applications. So anyway, in this talk, I would like to show you this field. The reason why we'd like to develop the ToF-based 3D scanner is here. In the conventional method, use active triangulation method, and in this method, we should have the baseline, that is a distance between the detector and the light source. And due to this baseline, the head size cannot be small. So on the other hand, the ToF-based 3D scanner, we don't need, the baseline is not required. So we can obtain your compact head, and occlusion-less 3D scanning is possible. And here's the merit of the ToF-based 3D scanner is working distance control. In the conventional method, the
the range precision is strongly dependent on the target distance. So to capture the 3D image, so the scanner head should be moved in z-axis. On the other hand, ToF device can control the working distance electrically, and also the range precision is independent of distance if received photon is constant. So high-speed capturing is realized. And also the additional feature of ToF device, potential additional feature of ToF-based 3D scanners is here. So here is an example of the material classification. This is obtained by distance distortion due to the interreflection and interreflection. And also we can obtain a much view scanning by using the mirrors. So these features leverage the unique properties of the ToF cameras, so enhancing the value of the ToF-based 3D scanners. So what should we solve to realize the ToF-based 3D scanners? So that is the improvement of range precision. As I said, the usual ToF cameras has several millimeter precision at best. So that is inadequate for the 3D scanners. So we have to improve the precision at least sub 100 micrometers. So here is an example with the iToF imaging by using the two-tap lock-in pixel. By using the lock-in pixel, the received light is modulated to 2 parts, and accumulate by calculating this equation, time of flight can be obtained. In this method, range precision is determined by 2 factors. One is the pulse width over the SNR, and the other is the jitter component. And ideally, the first term, SNR is determined by photon shot noise. So this is an analogy of the scale. The measuring range is determined by pulse width, and the number of scale is determined by SNR, and ideally equal to the square root of the signal electrons. So to enhance the range precision, the pulse width should be minimized, and the signal electrons should be increased. So to improve the first term, we propose the ToF measurement by using impulse photocurrent response. In this method, we use a short pulse laser that pulse width is almost 100 picoseconds. And this pulse generates the photocurrent like this. And then this, by using this photocurrent response, we can calculate the time of flight. And this equivalent pulse width is determined by the response of the lock-in pixels. So high-speed charge modulator realize the short equivalent pulse width. So we can obtain the higher range resolution. This is an example of the ideal calculation of the precision, range precision. So if the equivalent pulse width is equal to the 300 picosecond, we can get the 40 micrometer range precision. So this is our first prototype of our this time of flight using that method. And actually, the range precision is obtained. Equivalent pulse is almost 300 picosecond, but the actual range precision is limited to the 140 micrometers. This precision is limited by jitter components. So we should reduce this jitter component. So to reduce this jitter component, first we implement the reference plane sampling. In this method, the light source is divided into two directions. One is to the target and then captured by main pixel. And the other is to the reference plane and capture the reference pixel. And this reference plane is fixed and placed at placed to fixed distance and fixed distance and known distance. So the fluctuation induced in the reference pixels is the same as the corresponds to the jitter component, jitter in the light source, and that jitter, that fluctuation is same in included in the main pixel. So by taking the difference between two output in the time domain, we can reduce this light source jitter. And this is effective to improve the range precision. As a result, by using this method, the range precision is improved to be 64 micrometers. Here is our example of the 3D capture image without reference plane sampling and with reference plane sampling. By using this method, the clear point cloud can be captured. And this is example of the 3D scanning by taking the 5 different view angle and synthesize that point cloud. But we have a remain jitter that is a gate driver jitter, and due to this gate driver jitter, the large range precision has a large column to column variation like this. This is a vertical axis column and horizontal axis, vertical axis range precision and horizontal axis column. There is about large variation column to column. And also the range precision is limited even using the averaging, frame averaging. This is because this gate driver jitter has 1/f noise spectrum. So the averaging has less effect due to that spectrum. So to reduce that gate driver jitter, we first implement these techniques. We call the dual reference plane sampling. And this technique is very simple. We make a reference pixel for the column-wise directions. And by taking the difference, 1 minus 3, the gate driver jitter are same for the column. So by taking the difference, column jitter can be cancelled. And the additional jitter is induced in this method for this additional laser. So we can to cancel this additional jitter, we calculate the 3 minus 4. And by using this equation, all of digital components can be cancelled. And this is very effective to reduce the column-to-column variation. And also by using the frame averaging, the range precision is improved to the 20 or less over the 27 micrometers. But this method has disadvantage because we need additional laser to cancel this gate driver jitters. So we implement we developed another method, charge injection reference plate sampling. That is, we optical input in the dual reference plate sampling is replaced with charge injection. So we made a charge injection pixel in column parallel, and then charge injection pulse is input to this charge injection pixel. And by using this, charge injection pulse, the shared photocurrent is generated. And by using this shared photocurrent, we don't need the additional laser. And this is a pixel design of the main pixel and charge injection pixel. We made the charge injection part, and then by controlling this potential, the charge injection, we can generate the charge injection, shared photocurrent like this. This is our measurement example of the proposed method. And prototype is made by the 0.11 micrometer CMOS image sensor technology, and the sensor is line sensor. The result is here is the range precision is improved to the 41 micrometer for the single frame, and then by 10 frame average, 25 micrometer range precision is achieved. Here is a performance comparison between the other time-of-flight devices. Of course, it is difficult to make a fair comparison because other ToF device has a different target, but we have a good range precision, and also compared to the FMCW LiDAR, the precision over the distance is better than the FMC LiDAR. And this is a preliminary results for the accuracy measurement by using for the ball bar gauge. That is a standard method to evaluate the 3D scanners. And this by this measurement results, our accuracy is also obtained 63 micrometers. So accuracy, in terms of accuracy, we can achieve the sub 100 micrometer level. Here is summary of my talk. Thank you.